Okay, let's go through some MATLAB code to continue our drop jump integrating problem. All right, let me share my screen. Put together a MATLAB code. I put the code in a shared folder. Make sure you go to that shared folder, take those M files and put them in your MATLAB work directory. Take your data file and put that wherever you put your data to read in. I always put my data in a directory called C biomech, and then I have different folders for different projects. And right now I just have it under PhD, and there it is right there. Okay, so let's see, maybe I can zoom in. I don't know if hopefully you can see this okay. But you'll have the program in front of you. So let me go through the program and tell you what we're doing. I did start with Cordero's code, but I did take out a lot of it out. Sorry, Cordero. So I almost started over, but I did start with your code, and then I started removing and going a little bit different direction. So this first part, clear all variables, CLC, clear the screen, close all figures if there are any figures open. This is my data location, C biomech, PhD, and I just do a quick change of directory. And this is not Cordero. I don't know how you put those lines in, but that line is from you. So you see, I did start with your code, and then I just put information specific to the routine. Sample rate is 1,000 hertz. G negative 9.8 meters per second squared. FZ threshold, this is the threshold that I want to use to detect contact or takeoff. And again, I start with 20 newtons, and then if my ground reaction force data are noisier than expected, I'll adjust off of that. But I pretty much use 20 newtons as a default. Body weight 700 newtons. I'm not 100% sure if this is correct. I did go to another file. I was using, this is Cordero's data. So I did go to another file that was a counter movement jump, and I pulled the body weight off of that. So it's probably close enough, but if I was collecting these data, I would make sure to get body weight specifically, because and I would get it off the force platform, not off the scale in the lab, because then I'm reading the body weight off the same instrument that I'm recording forces from. So I'd have them stand on the force platform and even just record a body weight file if I need to do that. So a little bit of guessing on this. Box height, I don't know what the box height was. I'm just guessing at this as well, but this you would specify how high the box is for the drop jump. And then SI, I use that for initial position. I'm setting that to 0. So technically this would be the height of the center mass standing. So if you go below standing height, it's going to go negative positions. If you're going to go higher than standing height, it'll be positive positions. I just called, I just opened this up. I just did this for one file. So I just read this in as a file name. If I was putting this into a loop, I'd do this differently. But right now I'm just demonstrating based upon this one data set. Read the file in using XLS read, and then I go ahead and organize the data. Now, in this case, this data set had 2 force platforms, and one foot was on one force platform and the other foot on the other force platform. So I did just a total ground reaction force, and I just added those 2 forces together. Time, I created a time column because the data set did not actually have a time column. It had something else in row 1. It wasn't even frame number, it wasn't even row number, it was something else. So I just created a time column starting at 0, incrementing by sample rate, and then going to the length of the data set minus 1 data point, because I start at 0. Remember, 0, 1, 2, 3, 4. That's 5 numbers, including the 0. So I always have to account for that fence post error, I call it. And I divide that by sample rate, and then I'm in time in seconds. I always like to work with time in seconds when I do my plot. You're going to want to really, when you start trying to interact with the plot using G input, you're going to really want to pay attention to what you're putting on the x-axis, because that tells you, that will influence what your G input returns and what you do going forward. So I just get in the habit of trying to always put time on the x-axis, and then my thinking with using G input is always the same from program to program. So I'm going to plot the raw time. I'm going to plot the raw FZ. Good practice, label your figures right away. That way you have that already done. I'm going to turn the hold on so I can add some other things to this plot. Now I'm going to first extract the data set. So this, the raw data starts, 0 starts at some point while a person's on the box, and we don't know when the person starts to move, but then there's a data set then the data set includes contact and takeoff, and then flight phase, and actually another landing. And I'll show you that in just a second. So I have to, just like the other video I did on how to process the ground reaction force, you have to extract the data from contact to tow off. So let's see what do I do here. Oh, actually what I needed to do is trim the data, because the data do include landing from the jump. So the task is stepping off the box, landing on the force platform, immediately jumping up in the air, and then landing again on the force platform. And so I wanted to trim the data to get rid of the second landing. All right, so that's what this code is about. I get one data point. I tell the user to click during flight phase, and then I use that data point to trim the data from the first data point to wherever I clicked. Wherever I click has no meaning as long as it's within the flight phase. I'll show you that in just a second. I plot the trim data, and this way, this is something I do all the time to make sure I'm ultimately extracting the correct data. So I plot the trim data in green. I put a little pause in there so we can see it. And I always like to write information to the user so that the user knows what is going on. I put another pause in there just to hold. Maybe I better put, press enter to continue. And then I go ahead and identify contact and tow off. And you can see here, I'm calling this function, find heel contact tow off. Now, I actually wrote this years and years ago to find heel contact and tow off during running. Well, it's the same code for landing. And I'll go through that in just a bit, because that's an important set of code that you want to be familiar with. And you're certainly welcome to use that function, and that's one of the M files that I'm sending you. Then we go ahead and extract the data based upon the heel contact and tow off. And what this function does is it returns the row number for ground contact and the row number of takeoff. So now we take out the contact to tow off, put that into a new variable called FZ, and I do the same thing for the time. Now in this case, for time, I'm using the same raw time. So ground contact is not 0 at this point. And that's because I want to overlay this data set with the original raw data. And I want to confirm that I'm extracting the correct data. So I'm going to adjust this in just a bit. Data extracted to original plot. I didn't do it. Plot data extracted to the original plot. To confirm it worked. So plotting time and FZ, and I'm putting that in red, and just tell the user what's going on. And now we get to the integration part. First, I manage the figures. I close that figure upon exiting this right here. Once we've confirmed that the extracted data are correct. And I'll tell you, when I wrote the code, I actually was extracting the wrong data the first time. And I only knew that because I plotted data in green, and the green part of the plot was showing up somewhere else than I expected. I'm like, oh, what did I do? So I had to go back and fix my code. So it's hugely valuable to plot things on in your code. I adjust time now to start at time 0. So I take time and I reassign it to itself minus the first time. And that way, the first time becomes 0. Okay, real super easy way to do that. I calculate acceleration. And you know how to do this. This is the FZ minus body weight divided by mass equation. Oh, here's the mass right here. I just took the absolute body weight divided by G just to get that. Remember, I assigned G to be negative 9.8 meters per second squared. So that's why I take the absolute of that. Then go ahead and calculate the initial velocity based upon box height. And I use that equation. Now, the one thing I did not put in the notes is to deal with negative velocities. So when you use this equation, VF squared equals VI squared plus 2A delta S, and when you solve for either VF or VI, you do need to assign the direction of velocity after using that equation, because you do VF equals the square root of 2A delta S. Well, if you have a negative number inside your square root, you're going to get imaginary numbers. And so I just take the absolute value of that product, which will be negative, take the square root of it, and then I know the person's moving downwards at the moment of contact, so I assign it a negative direction at that point. Then I go ahead and integrate, and I use a function I put together years ago, where I send the function time, the acceleration data, and the initial velocity, which we just calculated here based upon box height, which is exactly what I explained in that other video. And I integrate position, or integrate to yield position. So I use that same function, same time. Integrate time V, and then I send it initial position. All right, so you can see all I did is I changed which variables I'm sending the function. And that's why it's really useful to learn how to use functions here. Then I go ahead and plot the data, position, velocity, acceleration, ground reaction force, and we set it down. I'll go through the other routines in just a second, but when I run the program so you can see it, and then I'll go through the two functions I call. So use drop jump 2020. And I'm sharing the screen, so hopefully you see the figure here. All right, this is the raw data. I labeled it raw data, ground reaction force, time, bunch of zeros. Person's in contact with the box here. We have no idea when the person steps off the box. No idea. I can't do anything with integrating the data with this zero, okay? Because there's another force acting on the person that I'm not accounting for. The person hits the ground, does a drop jump, and leaves the ground off into the air and lands on the ground again, and then ultimately stands still. They're still moving here because this is not a flat line. So my instructions down here say click during flight phase. So as soon as my program stops freezing, I'll go ahead and click anywhere. And I can click anywhere in here. All I'm going to do is use that click to get rid of these data to the right of my click. That's all I'm doing. So now I've got all those green data, okay? And I'm going to hit space bar. I've got an extra pause in there. Press enter to continue. And, oh, I'm missing, hold on, I got to go fix my program. But here are the position, velocity, acceleration, and ground reaction force data for the drop jump. All right, so let me go back up here. I dropped a pause here that I actually want to still have in. There's the green. Here's the red right here. This is where I need a pause. I'll do it again so you can see that red, because that really is an important part of programming and processing data. This is the same. I show which data have been trimmed. This is nice because, again, the first time I did this, I was actually just getting trimmed data over here. And that caused me to go back and look at the input file a little bit more. And I realized the input file was written different than I thought it was. And so I had to fix that code. And I hit space bar. Come on. There's the red data. That's the extracted data. Now it shows right up on the plot because of the way I treated the time variable at this point. All right. And that's just a nice way to confirm that I'm processing data that are related to the drop job. I'm not doing data over here. I'm not doing these data, anything. Okay, it's really important to do that. And then it goes and heads and does the integration. Okay, so this makes sense. The person hits the ground, goes down, up, and then off into the air at this point. Now this is higher than contact. So I have the wrong body weight for this person, because that doesn't make any sense that this person is leaving the ground almost a meter higher than landing. So I either have the box height wrong or I've got the body weight wrong. So those are two values that I guessed at based upon the data that I had. Well, here, this still makes sense. These are all negative velocities, slowing down, moving downward, speeding up, moving upwards. This acceleration profile looks just like the ground reaction force profile. Here's 0 right here. Okay. So this initial velocity is determined from the box height. So again, if I have the wrong initial velocity, it's because I've got the wrong box height. And if that box height was higher, this initial velocity would be down here, and all that would happen is this line would shift down. Okay. In fact, I can show that. I can go up here and I can change the box height. Let's say it was actually higher. I'll make it 0.5 meter high. All right. I'll run the program again, and you'll see everything will be looking the same up until the end. I'll trim the data. I still have the same extracted data. And now here's the position data, or here's the position, velocity, acceleration, and ground reaction force. Same ground reaction force, same acceleration profile, because I didn't change body weight. Now my velocity plot starts at a higher negative velocity. So magnitude greater, negative is the direction. And now you can see the position plot looks quite different. Starts at 0, goes down to some low point, and then up. And takeoff is about 26 centimeters higher than landing. So it still seems high. So something seems off. So maybe really I have the wrong body weight here, or I have both the wrong body weight and the wrong drop height. But now you can see that integration routine. Now let's go back and look at a couple of the functions. First function is find heel contact and toe off, or in this case, it's really ground contact and toe off. So use a function, and if you haven't used functions, let me know, because I can go back and spend more time on how MATLAB works for functions. This is what's going to be returned from the function. This is how to call the function. I send the ground reaction force and the cutoff or threshold value to identify contact. Just do some assignments within here. And this is the important part. What I do, and I explained this in my other video, I check to make sure that a series of data points are all continuously above the threshold. I don't look for the singular value above that threshold or below the threshold. In this case, I wrote it to look at 20 data points. All right, 20 data points greater than 20 newtons. I'm going to be pretty confident that that first data point is ground contact at that point, as opposed to just some errant value that's greater than 20 newtons. And then the next value is some, noise, like maybe even a negative value below 0. So I check to see if there is a continuous set of values that are greater than 20 newtons. So what I'm doing is parsing the data set. I just go look at the entire file, and then I go through the first 20 data points, and I check to see what the difference is between the second point and the first point, the third point and the second point, and so forth. And if that difference is greater than 1, then I assign that to a temporary heel contact. All right. If it's equal to 1, let me see here, then that's the same data point. I should have gone through this in more detail. I do the same thing for toe off. heel contact. Yeah, I haven't looked at this code in a while. So but what it's doing is it's setting up, making sure that there are continuous data points that are all above 20 newtons. And I do the same thing for toe off, but I do start one data point back because I'm looking for the first data point less than 20 newtons. And then finally, I do assign heel contact and toe off to those temporary values that were picked out as we go along. Yeah, sorry, I'll go back to the code, to this section again. All right, and then on integration, what we do, real simple code. I send the function the initial parameter, either initial position or initial velocity, and then I create this loop to go from the second data point to the length of the data point. And then I actually look backwards one data point. That's why I start at 2, because otherwise I run into a problem with doing the first data point minus 0, and I don't have that data point. MATLAB doesn't like that. So I start at the second data point, and then I look at the previous data point, and ultimately just calculate a rectangle here for the area. And then I add to it the previous data point. That's why that I minus 1, if this starts at 1, that would be 0, and MATLAB does not use 0 for an element number. C++ does, but MATLAB does not. So then I just I calculate the rectangle, and I add it to the previous rectangle or the previous sum at that point. And that's integration. It's simple. Now I could change this to trapezoid. I actually find that a rectangle, when we use high sample rates, a rectangle is fine. I really don't need to do anything more fancy than that. But you want to convince yourself, create 2 different integration routines, and then compare them. Okay, so then I come back to the code and continue to run it. And that's the advantage of using functions is, like me, you can forget what the code does. And then, but you don't need to remember the code, because you just need to remember what you need to send the function, and you need to know what it's going to return. Okay, I think that's it for this routine. Hopefully we'll generate some good questions and some discussions on this. All right, thank you.